Yeah, it's a huge challenge. It's certainly going to take at least another 10 years to
I
meet.
was going to say, you can't do this in 5 years? Come on.
Luckily, I feel like at least the pool of excited people who are willing and interested in helping me make progress on this is growing. People went from saying things to me like, excuse me, but does this have something to do with perceptrons?
This is Brain Inspired.
Welcome, everyone. This is Paul Middlebrooks, and if I sound a little different, it's because I'm recording this introduction on my phone because I'm traveling with the family currently in Flagstaff, Arizona, and I forgot to bring my good microphone, so I hope it sounds okay. I'm also recording this intro while my family sits and silently stares at me, waiting to go do, quote, fun stuff. Right, guys? Well, still, just silently staring. Okay, a few things before I introduce today's show. First, thanks to all my new supporters on Patreon: Daniel, Joe, Tim, Peter, Gabriella, Omri, Kulin, and Lindsay. Thank you guys. You really don't know how rewarding it is to know that you appreciate the show enough to support it. If you would like to support the show, go to braininspired.co and find the Patreon button there, where you can give as little as $2 per month. If this support continues to grow as it is, I will be able to start paying someone to edit the show and do other sundries that'll allow me to focus more fully on the content itself. And it'll free up my time a bit more to start producing some supplemental content, maybe a little mini course down the road. And if you're supporting the show, then you will definitely have early beta access to that when it happens. So again, thank you for the support. One other thing, I want to welcome you new listeners visiting from Ginger Campbell's podcast, Brain Science. I hope you find something here useful, perhaps even inspirational. So Brain Science, Ginger's podcast, is a long-standing, excellent resource if you're looking for broader topics on neuroscience and the likes. Ginger has an interest in consciousness and understanding how our brains give rise to consciousness, so she has a lot of guests that focus on that, and those are some of my favorite episodes. But she also covers basically everything under the sun that has to do with neuroscience, with philosophy, psychology, and so on mixed in. So you should check out her show at brainsciencepodcast.com. Like I said, she interviewed me most recently about my background and deep learning in general to introduce that topic to her audience. And we talked about my little show here. And I was delighted to contribute a bit to her show. But I recommend you check out her trove of past episodes where you'll recognize plenty of names and discover lots of other great topics that you'll want to listen to. Okay, today I bring you none other than James L. McClelland, whose name is inextricably linked to the concept of parallel distributed processing, or PDP. PDP is basically a synonym for what has been variously called neural networks, connectionism, parallel distributed processing, and now deep learning. Jay has been a champion of the idea that learning done in PDP networks, that is, symbolic, distributed processing over simple units, can underlie virtually all of our cognition. So we talk about the history a bit, the passing of the torch from symbolic-based AI to the PDP neural network approach, and you get to hear how Jay experienced that rather prickly time. You'll hear him reference a famous past tense debate that he and David Rumelhart had with Steve Pinker and Alan Prince, and later others, about whether the past tense of verbs are formed using a distributed neural network-like coding or a more grammar-specific rule-based type of coding. So you'll hear when he's talking about that. His earlier work focused on lots of cognitive science, like language and reading, as you just heard. semantic cognition, decision-making, and quite a bit more, actually, all under the PDP approach. And much of that work was done with David Rumelhart, with whom Jay published the famous and still thought of as a sort of Bible for neural network PDP approaches, the book Parallel Distributed Processing from 1986. That was then, and this is now, and his newest project is trying to tackle mathematical reasoning in machines. It's worth here describing this briefly before we talk about it in the show. Jay has set himself the goal of producing an AI agent that can pass an official New York State geometry exam, and to do so in as human a way as possible. That is, to learn through exploration and feedback and reinforcement, and to be able to explain how the agent came to a certain answer, and for the agent to ask for explanation of why a certain answer was the right one. So a rather ambitious project, which, as you'll hear, Jay is well aware of. We talk about how his approach differs from the kind of learning that DeepMind has successfully implemented, which largely relies on reinforcement learning, but not as much on other aspects of learning. Jay talks about how he's come to think that language itself might be important for accomplishing the goal of passing that geometry test. So that's pretty interesting. We reference and discuss at some length some of the work that I talked about with Sam Gershman from a couple episodes ago. Sam and his colleagues argued about how our current deep learning approach leaves out important human skills that we somehow need to include if we want machines to really emulate humans, thinking-wise. Jay talks a bit about how his approach differs in that he maintains we can do just that, but without hardwiring in the human-like abilities, but again, figuring out how to do it from a lower-level neural network-like approach. So I recommend listening to episode 28 with Sam if you want a bit of the background on that. I also recommend, if you want to learn more about Jay's mathematical reasoning project, to watch his lecture in which he lays out the project well. And I'll link to that in the show notes at braininspired.co/podcast/30, along with many of the other things that we've talked about in this episode. Daphne, if you are listening, my apologies. One of the topics I wanted to discuss with Jay is the learning theory that he developed many years ago in 1995 and has recently updated. It's called the complementary learning systems theory, but we just didn't get to it. Jay had other pressing matters to attend to, and I wanted to let our discussion take its own course a little bit. So it's possible, and hopefully I'll have Jay back soon to talk exclusively about that. But I do also have some other guests lined up to talk about learning as well. So hang in there, Daphne. We will get there by hook or by crook. All right, my family's rolling their eyes now, telling me to finish up. So thank you for listening. And here is Jay McClelland. Jay, thank you for joining me and agreeing to teach me today how to do better math.
Okay, well, I'm willing to give it a try.
So I'm actually tempted to say that you need no introduction and therefore give you no introduction. Do people ever actually do that because of how well known you are?
Sometimes they say this man needs no introduction, but usually they say a few words.
Okay, well, I guess I'll say a few words here. I will have given you a proper introduction before we've actually begun recording here, but extremely briefly, you're the director of Stanford's Center for Mind, Brain, and Computation, and you run the Stanford Parallel Distributing Processing Lab. And I will have gone through many of your accomplishments and interests from your past, but today we're going to talk a little bit about the history of parallel distributed processing and AI. We're going to talk about the complementary learning system theory that you've developed and how it relates to brains and AI. And your current big focus project on implementing mathematical reasoning in machines. And then if we get through all that, time willing, I'll ask you some broader questions.
Sounds good.
Before we begin, though, I would like to extend a personal thank you for helping found the Center for the Neural Basis of Cognition, the joint effort between the University of Pittsburgh and Carnegie Mellon University, where I earned my PhD. So thank you, sir, for helping found that institution.
Oh, that was definitely my pleasure. That was one of the most exciting opportunities I've ever had.
Very good. So before we dive in, let's just play a little Name That Year quiz here.
Okay.
Okay. So I'm going to name the event, and you name the year that you think it happened. Are you ready?
Okay.
All right. So what year was the first PC virus called Brain? Did it come to be? What year? I guess, did it infect PCs would be the correct question.
Oh, gosh. Being a cognitive scientist, I have no idea. Maybe 1982.
1982, okay. What year did Chernobyl, the nuclear power station, explode?
Was that also in the 80s? I want to say it was 40 years ago or something because it was recently in the news. So it would be 79?
79. 79. We'll go 79. How about the Space Shuttle Challenger exploding shortly after takeoff?
I just watched the movie about Armstrong, so I'm going to have to say 66.
66, okay. We just have two more here. One is, when did Peter Gabriel's Sledgehammer explode onto the scene and top the charts? If you know who that is.
Just barely.
Yep. I didn't say it'd be easy.
I'm going to take a pass on that one.
Okay,
I have
pass.
no idea.
And finally, when was the book Parallel Distributed Processing published by David Rumelhart and James McClelland?
1986.
Okay, you got that one right. And the answer to all of these was 1986. So apparently
really?
You were focusing on your work at the time, which is a good thing. So let's talk a little bit of history of parallel distributed processing, or I'm just going to say PDP now. So from roughly the 1950s into the 1980s, good old-fashioned AI ruled the AI world with symbol manipulating systems. And their argument was that this is how intelligence happens. It happens by manipulating symbols. And a symbol, when I say symbol here, I'm referring to a physical pattern that can get combined into structures, and then those structures can be manipulated. Then along comes an alternative approach, the PDP approach, which argues that representations occur over a spread of activity of relatively simple sub-symbolic units. So they're not symbols, there's these sub-symbolic units. In other words, it looks, more like the way that brains look. So this approach, this latter approach, has gone by various names: parallel distributed processing, connectionism, neural networks, and these days it's kind of all called deep learning. And I'm just wondering if you have a preference between those and what your thoughts are on the current term, deep learning.
I like deep learning, but I think neural networks is a good summary term for everything in this space, because deep learning is a method for training multi-layer artificial neural networks, and PDP models were always essentially neurally inspired or neuron-like processing units networks. Connectionist models was another name that was popular back in the 80s, and I think the focus there was on the idea that the knowledge wasn't stored explicitly in patterns, but was in the connections. And I find that notion very important, but I think the word connectionist somehow doesn't otherwise communicate too much to the audience. So I think neural networks sort of tells people basically that one is dealing with something that might have something to do with how the brain works, and exactly how much and to what extent and how much we should care is always part of the discussion.
Yeah, see, I tend to agree with you. For some reason, I think that the deep learning term is somehow misleading because it's come to encompass so many different variations of the neural networks. So, this is something I'm just wondering how long the term deep learning will last,
Well, it has a nice ring to it. It sounds like it must be profound.
That's right.
So,
well,
you say you're in deep learning, and everybody nods. It's like, oh yeah.
Oh boy, he's deep. Yeah.
Yeah.
Well, okay. So there was this passing of the torch, wherein the PDP approach basically emerged victorious. And this is chronicled actually in a book by Terry Stanowski, and Terry's been on the show, and he wrote The Deep Learning Revolution. And in that book and in other chronicles of this time period, it seems like it was kind of a tumultuous passing of the torch, I suppose. I mean, so was this downfall, if you will, of symbolic AI and the uprising, if you will, of PDP, was it as tumultuous as it seems now when people talk about it?
It was tumultuous to me. It's partly because I engaged with some of our colleagues at MIT that I can say that it was tumultuous, but I'm sure Terry told his story of his trip to MIT in his book.
He did.
And my story wasn't all that different than Terry's story. So
oh, wow.
I would say this. I would say that my experience of the period from, well, in my case, it was 1982 to maybe 89 was of a period where it gradually became realized that there was this new game in town, and people went from saying things to me like, excuse me, but does this have something to do with perceptrons? To writing articles where they were trying to explain why this whole approach would never really fly.
Right.
But by the time we got to 1988, I think my view would be that there was kind of this entrenched recognition that, okay, this is sort of going to be here to stay, but there was also a very strong ongoing resistance, and it wasn't by any means. It might have been one of the strongest computational paradigms in town, but it wasn't the only way people thought about cognition. There were many people who, if you read the literature from the developmentalists through the 90s and even up till 5-6 years ago, the papers are full of such statements as, when does the child discover the insight that leads them to answer this question correctly? And I'm like, well, why do we have to think that this is some sort of explicit cognitive realization? Right. So my feeling is very much that a new paradigm was put on the table and a bunch of people joined in and participated, but it was only one among many sort of competing viewpoints throughout let's say the 90s. And then there was this very big lull of interest in these things in the late 90s, early 2000s, when, AI turned away from trying to use backpropagation. I was told when I got here to Stanford in 2006 that they'd stopped teaching backprop in their core machine learning class in the computer science department because it wasn't useful anymore.
Wow.
So that was interesting to me, but it wasn't too many years later that changed again.
Yeah. Well, it's back in full force now, for sure.
Yeah.
Well, so were you guys getting invited to MIT just so people could badger you? And
oh, absolutely.
Yeah. Oh my gosh.
So there was this wonderful experience where I was invited to be the featured speaker at an evening seminar. And the way the evening seminar was supposed to work was that somebody from the MIT community, there would be a paper that would be circulated and people would be expected to take a look at it. And then somebody from the MIT community would sort of introduce the issues in the paper. And then this person who had written the paper would then get up and give a short overview of their perspective on the paper. And then there would be a general discussion. But what actually happened was, two people decided they needed to comment on my paper, and each of them took a full hour.
Oh, God.
So before I got a chance to speak, 2 hours had gone by, and, there needed to be a bathroom break, and everybody left at the break. So, and I was sitting there listening to these guys as they were the first one was Steve Pinker, and he was telling me that this was very important, everybody, that this was important. It's the first model that really took seriously looking at the data and modeling the phenomena rather than just sort of talking in very general terms and so on, and really liked the work for that reason. And then he would say, but, this is wrong and this is wrong and that is wrong. So it's great to see this thing out there, but these are the reasons why it's wrong. And then the next guy got up and he was basically like, don't even bother me with this stuff until such time as you show that this network can actually achieve adult competence.
Wow.
Right? So a competence-based critique, which says that the core of the computational idea has to be a structure that captures competence without error, and then the errors are these sort of performance factors that get in the way, sort of there's some noise somewhere, but if you took the noise out, you'd be able to show it would do it perfectly. So don't even talk to me until you have that.
I guess you haven't talked to him yet.
Well, he's still alive, and he's still, a guy who's willing to practice rhetorical techniques that not everyone appreciates, but it was also a perspective that, sort of represented the Chomskyan kind of core idea that competence and actual behavior had very little to do with each other. And, that nobody ever collected a data set when any human adult correctly inflected the past tense of every single word that was presented to them, so it's an ideal that it would even exist. Some model that would do that. But
well, you're kind of referring to your famous debates with Steve Pinker, about the past tense and how that can happen, which we won't get into. But okay, so that's pretty interesting.
But it was at the heart of the whole debate, right? And Jerry, so I don't know if you know the book that Pinker edited, which had essentially the two speeches that those two guys presented, Pinker and Prince. And then this other critique by the guy who asked me if this had anything to do with perceptrons. And then finally, and most importantly, the critique by Fodor and Polishin of the entire connectionist enterprise. It wasn't just about a specific model. It was about the whole nature of the enterprise.
Well, so there's a lot of competition in science, as you know, right? And a lot of the rivalries, I've experienced them, can be ugly, even petty. They can get petty. On the other hand, they can also drive progress and innovation. And I'm wondering if, how your experience with that and moving on with other experiences, how that's shaped how you view, what, if you could set up sort of a competitive rivalry, what would be the optimal setup for it? It wouldn't be bickering, obviously, but a little competition is probably good, right?
Yeah. Well, so I'm going to answer this question twice. So first of all, what in terms of making a practical, concrete progress towards, sort of achievable milestones, one of the things that I've done repeatedly over my career is to find instances in the literature where somebody has made a claim about the nature of cognitive abilities, which I think is perhaps a useful first approximation, but actually not 100% accurate. And this is very much related to the past tense debate. It has to do with looking at the world through what in that instance I would call rule-tinted glasses, but in other instances I would call glasses that are tinted by your theoretical perspective such that you see the facts in a certain kind of way, and you characterize them in that way, and then you specify that in order to address the facts in this domain, you have to exhibit properties X, Y, and Z, where properties X, Y, and Z don't actually hold in the real phenomenon in the way that they've been stated, at least in the way these ideas get passed around. And so what I do is I come to these debates and to these aspects of the literature, and I revisit the data, and I try to bring out the ways in which they don't actually fully support the stated summary claims. And then I use that as leverage to illustrate the benefits of the approach that I take because it tends to capture those ways in which the phenomenon differs from the way it's been described previously in the literature.
This is almost a philosophical approach to revisit almost the meanings of some of the terms being used and the assumptions being made, right?
Yeah. So when somebody says that children have a eureka moment where they discover the past tense rule, and they kind of argue for it in terms of a statement about the data, that's when I go back and I look at the data in more detail. So we completely reanalyzed the data that backed up a statement about how abrupt this transition was. And we showed that, in fact, if you looked at it carefully, there was no abrupt transition at all.
Yeah.
And this then plays into the rationale for having an approach that doesn't sort of begin with the stipulation that cognitive abilities are a matter of acquiring discrete rules or principles that suddenly change the whole pattern of your behavior with respect to a whole domain, and puts us in a place where we can understand how a real wet biological system that kind of has a certain amount of intrinsic inertia to it isn't necessarily going to suddenly turn on a dime. It's going to require a certain amount of practice and experience to acquire new skills and abilities and things like that. So anyway, so that's been a part of how I would do it. I would identify these places where things have been misstated, re-examine the phenomena and lay out the facts again from another perspective, and then show how neural network kinds of models could address those phenomena. That was one of the two answers.
Yeah, okay.
I would say that the second answer relates to the deeper question about a long-term choice of research focus. So in my case, I decided to focus on mathematical cognition because it seemed to me that mathematical cognition was a perfect domain within which to try to achieve a real flip in the way we think about things. So, I guess fundamentally what I feel like my goal is as a scientist is to get people to think differently about things that they tend to think about in ways that, may just be sort of stamped in by history and habit. And, in mathematical cognition, there's a huge amount of emphasis on symbolic systems.
Right.
And the idea that math could be reduced to a completely logical system, a system of rewrite rules, something like that. And I just, I realized on the one hand that neural network models could often be seen as models that would capture the intuitive or implicit aspects of human cognition, but not the sort of advanced scientific aspects, the kinds of things that, we get PhDs to study, right? Like mathematics or computer science or physics or something like that. So, you could easily have said, okay, so we share this sort of basic biological architecture for, let's say, visual processing with many other animals that have to navigate in the sky and on land and swing from tree to tree and precisely grasp objects as they're moving through space and recognize things to distinguish food from poison and do all kinds of things like that, and even sort of learn, intuitive concepts through immersion and exposure to, discourse, like discussion about things or language. And, so implicit learning of linguistic knowledge through gradual connection adjustment. Okay, maybe that's all fine. This is all the stuff that, happens before we go to school, right? We learn our language. We learn how to recognize objects. This is all natural cognition. We learn how to move and walk and, even carry out fairly intricate motor sequences to tie our shoes and feed ourselves and so on. But when we get to school, we suddenly start being, this sort of formal systems come in. And, so the question, could neural networks help us understand both, on the one hand, why the acquisition of those systems is sometimes hard, but also, on the other hand, how it is that we somehow sometimes achieve brilliant sort of insights that don't seem to be, just building up connections by rote, but somehow learning to have intuitions that guide us to imply these interesting symbolic frameworks to new domains and to find, demonstrate that it's true that some principle really does hold or something. So it just seemed like an opportunity to turn the whole business on its head a little bit and ask whether, rather than thinking about symbolic cognition as the core characteristic of the human mind, could we see it as something that the human mind could learn to master as a tool that would give it additional power to exploit its intuitive and implicit knowledge abilities together with the capabilities of symbolic processing?
Maybe what we can do is actually, for now, just move on and talk about that project, since we're already kind of getting into it. But before we go there, so there's been a recent kind of backlash to deep learning, and a lot of people are saying that it's just not enough to get us to general AI, and this has to do with what you're just talking about. It's not really thinking like humans think. I had Sam Gershman on the show recently, and he co-authored a paper with colleagues, and they argued that we need to build in some human-like processes, like intuitive physics, like these things that we seem to come in the world with, right? Ready, like causality, compositionality. And you guys actually commented on that paper, and, you acknowledged, like, okay, this is going to take a long time to address here, these issues that you've raised, but building these human-like processes into the system is actually a limiting sort of shortcut that isn't how humans learn. And I'm wondering if this is a trend that you've seen since the early days and up till through all your work up to now, where you get to this point and people say, oh, well, now we need to build in some symbolic structure to it. Now we need to build in something that's not sub-symbolic, something above sub-symbolic, right? Is this something that you have experienced and, resisted all along, or what?
Yes, I do resist that. What you said is exactly what I would say. If you build it in, it's not so surprising that your model doesn't require as much experience to learn something.
Yeah.
What I find really intriguing, though, I read, of course, I'm very familiar with the article that you mentioned. We did write a response to it, and I assign it in my class, and I discuss it. And the points that are made in it are important points. They do a valuable service to the field by articulating some of the ways in which contemporary models, don't capture aspects of human reasoning.
Right.
And I'm always in favor of that, right? If you point out to me where the shortcomings are, I'm glad to know it. Well, I already alluded to this a little bit before, but what I really don't like is when you then go on and tell me what I have to do to solve the problem. And that's always somewhat motivating to me, though. Yeah. It's sort of like, okay.
Well, this gets to the competitive process here, right?
That's right. So these guys did a good job of sort of setting up some of the targets that we ought to try to meet in order to address the set of issues that we'll need to address before we do have anything like general intelligence. And so I don't have any objection to the observation about how different, a DQN is from Brendan Lake in terms of its ability to learn how to play Frostbite.
Right.
But, what's the diagnosis of the reason for that difference, right? And what's the right research approach to take to address that? So, if you want something that's going to work tomorrow, I think doing what Brendan Lake did in his dissertation, which was to explicitly build in the specific constraints that describe how the use of a writing implement would constrain the production of handwritten characters into an explicit generative model, that does give you a tremendous amount of inductive leverage. And that, part of the argument in the article was that that's what you need in order to account for the fact that humans are able to learn after they've just learned how to produce one alphabet properly. They know how to judge whether something is a character in another alphabet, or whether two characters are the same character or different characters, and things like that. So this is a very concrete and explicit sort of challenge that Brendan laid before us. Can we produce a general purpose learning system that acquires this knowledge such that it can do the generalization from only one previous or a couple of previous
examples,
alphabets that it's learned?
Yeah.
So I do agree that this kind of back and forth laying the challenges on the table is, very important. It's what drives DeepMind. They take up a challenge.
Yeah.
If you tell them humans can do something that their agents can't do, that's a research program.
Right.
Got it.
Yeah.
We ought to do that because humans do it and our machines don't, right?
Right.
Everybody, and if you can quantify this, you can sort of give a measurement. With this much experience, humans could do this much generalization. And here's our model. It needs 100 times the experience to get anywhere near that kind of generalization. Okay, that's a challenge we ought to address.
Yeah.
Right? You've quantified a difference between humans and current state-of-the-art machines. And that's part of what, really makes DeepMind go. There's something where humans are better than what's currently achievable. And so to learn what the essence of the requirement of an artificially general agent would be to address it, you need to, address that phenomenon.
Well, so far that's been games. So,
it's been games,
yeah.
But I think you can quantify it not just in terms of eventual success, but rate of uptake. How quickly can you master the new game? And it's been a little bit of an uphill battle for me to sometimes convince people that that's a worthwhile challenge to take on. But I have seen a certain amount of buy-in on that. And I think we'll see more, because we get introduced to new things all the time. We have to pick up on new ideas. We have to start using them pretty quickly. And we can't, always wait for 100 billion training examples with a completely balanced data set and so on to make progress.
Yeah, actually, it's not my intention to fuel any competitive spirits here today, but let's talk about your 10-year plan here to pass a math exam.
Okay.
So I know that you have a passion for helping human students learn math better, and trigonometry specifically. You also have a passion for helping machines learn mathematical reasoning. And this is your main focus now, which is to teach a machine how to mathematically reason and to do it within 10 years. Now I know from experience that when I've estimated how long an experiment will take to really be as accurate as possible, I then have to multiply my own estimate by at least 2 to be, nearly accurate, right? And you've talked to Jeff Hinton about this, and he doesn't think you can do it in 10 years. Do you guys have a wager on this, by the way?
Oh, no.
Okay.
I gave myself a 10-year horizon, not because I thought it was necessarily achievable, but because I felt that it would take at least that long at minimum.
I see.
And when I first had this idea, I figured 10 years was a reasonable expectation of my possible future time available to pursue the challenge. Now that about 5 years has passed, I know for sure that it's going to be another 10 years before it was successful. But that just means it's beyond the foreseeable horizon of what's actually doable based on what I currently understand. So maybe that's a better way of saying what I meant by this 10-year research program. I will say this. I feel like, well, I don't want to overstate this, but one of the things that's fascinated me over the years is the extended latent phase of learning in deep neural networks. So when you train a deep neural network, there are these long plateaus. Sometimes they're less visible than others, but oftentimes they're very visible, and they show up especially in reinforcement learning agents. A very, very long time goes by before it seems like the agent is beginning to learn anything.
Yeah.
And then all of a sudden, there's this fairly rapid transition that occurs. Now, obviously, there's some state of the system that it's built up over that long latent period that's sort of made it ready to make that more rapid transition. And I'm sure that there are many, many aspects or facets to that, but we now actually are beginning to understand exactly why this occurs in what we call deep linear neural networks. Anyway, this is a bit of a digression.
Sure.
But since I've seen this so often in so many domains of modeling cognitive development, I kind of feel like, okay, well, it's sort of expected in my foray into mathematical cognition that it'll be the same way. There'll be this long latent period before anything comes out the other end of the pipeline. Well, I was going to venture to say that I think you'll start to see more coming out, but I shouldn't. I don't really think that it makes sense for somebody to try to predict the future. I'm not a predictor of the future. I'm somebody who tries to make a long-term plan for what he might try to achieve in the future.
Well, you have, on your website, and I'll link to this, you have 3 videos where you lay out this project really nicely and clearly. So maybe we can just start with, the motivating questions that are driving you toward this project. One of these is, can networks really think? And so it makes me wonder, what is thinking? And you kind of argue that mathematical reasoning can be taken as thought.
Yeah, I think that's fair. I guess we could debate it, but it's hard to imagine that anyone would claim that Einstein didn't spend a hell of a lot of time thinking while he was developing the theory of relativity.
Right. Well, he was a very visual thinker as well, which pertains to some of your other material here. But,
yeah. So, but also, you think about Euclid and Archimedes and anybody who's trying to solve a mathematical problem or do a mathematical derivation, obviously it's also true when you're trying to debug a computer program or write a computer program or devise a solution to a problem where there seem to be constraints that you're having trouble figuring out how to meet all at once. So I think of thinking as being very much a process that is extended over a period of time from the time in which a problem is originally sort of envisioned as one worth solving to the time in which it's been formulated more specifically as a concrete and explicit sort of item to resolve, and to the time in which it's been, a sketch of a solution has been worked out, to the time when you've actually sort of fully consolidated your own understanding of the nature of that solution. And I feel like I've undergone this kind of series of stages of thinking myself. And I feel like Darwin went through these kinds of stages of thinking over the very extended period of years when he was, going from recognizing that none of the existing solutions to the problem of evolution made any sense to, getting really excited by an idea that he knew was somehow relevant, but he couldn't exactly figure out why, to then kind of like seeing how that idea worked and how it would result in, selection of traits that were more likely to lead to survival, and then going through this extended period of like doubting that could possibly be sufficient and so on. And so there's beautiful books about this that I've read some of. And in my own thinking, I went from thinking, could I ever build a neural network model that would capture aspects of human semantic cognitive development to having a closed form mathematical formulation that actually helps me see how the kinds of U-shaped developmental phenomena and stage-like transitions that occur in semantic cognitions could actually be understood, from a closed-form mathematical point of view. I mean, that's something I did over a more than 20-year period. I started being interested in semantic cognition early in the days I was working on complementary learning systems themselves. The complementary learning systems was maybe a starter. Maybe we should come back to that, But anyway, 25 years, and now I feel like, okay, I got an understanding of what was going on in all that work and why we were able to explain all those phenomena and so on. It's not something I can do on my own. It requires a group of people. It requires people whose mathematical skills are stronger than mine. And it sort of motivates me to think more about helping other people learn mathematical ideas, because I still struggle when I have to learn the new mathematical ideas that then allow me to understand my own models.
Well, that's what another one of your motivating questions is, why is math so hard? And can neural networks help us understand how we do learn math, right? So to maybe make it easy.
It's easy to understand why they would explain why it's hard, because they learn so damn slowly.
Yeah, right.
So Sam Gershman and colleagues would agree with me about that. Okay, yeah.
But
neural networks explains why math is hard, but they push back and say, well, I'm not interested in what's hard. I'm interested in what's easy. And I'm like, well, okay, but you kind of like get to what's easy after you've been through what's hard.
But so then the final motivating question here is how to extend neural networks to capture this math cognition. So what you're saying is essentially is that what we have right now won't work, and we have to extend it in some way. Now, that's not just building in symbolic math concepts, right? You want to do it on a sub-symbolic level. But it's an admission that, we're going to have to develop different approaches to the networks, correct?
Well,
admission's a strong word here, but
I think actually my response to that might surprise you a little bit. In that paper and in the lecture, I hope, it's certainly in the paper,
laying out this project,
laying out this approach, I talked about the role of culture and structure in experience might play in this. And as I've continued to think about these things, I've begun to feel more and more that the fundamental limitations are not as much in the architectures, but more in whether our neural networks are placed in the same rich experiential context that human learning occurs in. So I can say three things about this specifically. One of them is, and I think this is possibly the most important, we use language to share ideas with each other and to allow things that have been discovered gradually through experience to be transmitted quickly through a linguistic statement. And the neural networks that play Atari games or Go or chess have no language at all. They just have a bitmap and a response, a set of response options. And it's quite amazing that very advanced skills within the context of these games can be achieved by these systems, but I firmly believe that one of the things that we do achieve in the course of the first 2 or 3 years of life is an ability to let language guide our behavior and our thought processes, and let ourselves even use language to gather additional information from others. And this needs to be a part of the way any system that's going to acquire productive conceptual knowledge learns. I think it's going to need to have this ability to utilize language input to guide its behavior and utilize linguistic input to output to explain and ask for explanation on the output side. So it may be that there is some missing architectural element that will be required to allow that to happen. And I don't want to claim there aren't other architectural innovations that are going to turn out to be relevant and important. And, every year some clever new innovation occurs in deep learning, which I think is useful.
Well, yeah, these are like the kind of the bells and whistles that even DeepMind uses, the DeepQ network uses, is, reinforcement learning plus experience replay, which we would talk about if we talked about the complementary learning system theory too. Maybe before we move on, we should just talk about so you set some concrete goals for the project, and I started off by saying how to teach a machine to pass a math exam, but the goal, one of the concrete goals, is to teach a machine to pass the New York State Regents exam in geometry specifically. So that's a nice concrete goal, and not only that, but to do it like a human, so that can it learn and function and explain its own actions in a human-like way. So
right. So I think that last statement, explain its own actions in a human-like way, really taps into what I was just talking about, right?
Right. Yeah, exactly.
It turns out that the is written in English, right? There are sentences.
Yeah.
And there are diagrams, and there are formulas, and there is graph paper. I mean, it's interesting in that regard. So in order to take this exam, you need to be able to read graphs and draw graphs and interpret diagrams and understand text and mathematical expressions and manipulate mathematical expressions and even state the basis of your reasoning in explanatory statements. There are questions that are graded by human graders that require these kinds of explanatory answers.
Yeah.
So, there's only a few of them because that's obviously a time-consuming task for a human grader for each New York State Regent exam taker. But it's also part of the challenge, and it relates to what we were talking about, which is that I need to have an integrated skill set that involves being able to see how the same relationship can be expressed in a sentence, in a formula, in a diagram, and connect those to each other, which is what I think people do. So it needs to take language in, it needs to produce language out, it needs to look at diagrams presented to it in a visual input, and it needs to manipulate them and construct new ones. So in some ways, it's got visual, motoric, and linguistic capabilities, as well as the ability to properly process symbolic expressions, according to structure-sensitive rules, while also relating them to the problem at hand and going from the problem statement to the correct formula and vice versa. So, yeah, it's a huge challenge. It's certainly going to take at least another 10 years to meet.
I was going to say, you can't do this in 5 years? Come on.
Luckily, I feel like at least the pool of excited people who are willing and interested in helping me make progress on this is growing. And maybe this podcast that you're producing will recruit one or two more excited individuals
or scare the hell out of them to run away.
Yeah. Well, at least it's a challenge that could potentially be met.
Yeah. So we have maybe 8 more minutes here. So it's too bad because there's the complementary learning systems theory stuff is fun, and it's neat that it's been updated from 1995. This really influential paper. They're really kind of minor updates actually. It's still looking good, going strong here. So I might. Okay, I'll just take that laugh as a confirmation. So I might describe a little bit of it and in the introduction and link to it in the show notes. And if we need to, we can have you back on and talk about it more fully as well. But
okay.
So let's talk about just some broad things. What's one instance where luck has played a role in your career or work?
Meeting Dave Rumelhart, being a colleague of David Rumelhart, was probably the best thing that ever happened to me in my life, in my scientific life. Anyway.
And you chalk that up to luck.
Well, the process of which academic job somebody happens to land is definitely a matter of happenstance, at least. There were particular reasons why I was the candidate chosen for that job and not somebody else, but it was luck that he was there at UCSD. It's part of the group that decided to hire me in some level. And, I think it was more broadly, I think Don Norman and Dave Rumelhart provided a context where being serious about the cognitive psychology while also being really open to both mathematical and artificial intelligence research was, really, considered a cool thing to do. And I really felt it gave me the opportunity that almost any other psych department job anywhere in the world wouldn't have opened up to the same extent. Just the opportunity to sort of think not just about the empirical phenomena, but also the deeper computational kinds of questions about how you could actually build systems that implemented them. Maybe Carnegie Mellon would have been about as good, and I ended up there later, so that was fine.
Right.
But for me as an assistant professor, the opportunity to think with Rumelhart in particular was also just truly amazing.
Yeah.
And I thought that was a very fertile bit of soil that I landed in as an assistant professor.
I know he was a well-liked individual as well. So I'm reading this book by Hasuk Chang called Inventing Temperature, and he extols the virtue in having a long-term focus, kind of a singular not singular necessarily, but a long-term focus. And like you're talking about with Darwin, going back and thinking about it over and over. And I think kind of like you've done in your career here and what you're setting yourself up to do within 10 years, of course, with this math project. And I'm wondering what you think is the right balance between, this singular kind of focus and diving deep on one thing and keep scratching and clawing, or moving around and exploring, this exploration versus exploitation within your career sort of question,
Yeah. Well, I could talk forever about this kind of question.
Well, you don't have forever, so.
Right. I guess what I would say is I do find myself to be spread quite thin. I do have a sense of myself as somebody who has moved from topic to topic. I would say that typically what happens in my case is that I work on a topic until I reach the point of feeling that what I wanted to learn from working on it has been learned. And so that's when I move on from one thing to something else. I guess the other thing I would say is that this sort of broad goal of developing a simulated neural network agent that can pass the New York State Regents exam is so extended that it has to be broken down into multiple sub-goals. And so the lab has been, I can at least say this, after a couple of years of not producing anything, we've begun to produce,
Great.
Some papers sort of making small dents in this problem in little ways. And in each one of those cases, we're biting off a little chunk of something that you might see as kind of like part of this huge elephant. or not, but at least I see it as part of a huge elephant and part of working towards that broader goal. So there's definitely a diversity of, like sub-domains like geometry, trigonometry, early acquisition of number, understanding fractions. These are all domains in which people, spend their entire career.
Yes,
right?
yeah.
But nevertheless, there's so much common structure about, what kinds of mistakes people made, what's hard or easy to learn, what's why, et cetera, that I just feel like finding out more about any of them is sort of contributing to my deeper goal of understanding how to make progress on all of them. So from that point of view, mathematical cognition is very exciting and very, very diverse as a overall field to be dabbling in, while still giving me a sense of underlying sort of organization to my efforts.
Yeah.
So, yeah.
Well, so lastly, Jay, if you were going to start over, if you were just getting into AI and neuroscience just now, what approach would you take?
Oh, wow.
What advice would you give to your niece who's interested in getting into this stuff?
I would tell her to do two things. I would tell her to find a collaborator or at least a mentor to bounce ideas off of. And I would tell her to try to find a specific problem that exemplifies a larger issue. So a specific, concrete, solvable problem that exemplifies a larger issue. I think that this is the interactive activation model, which is the project that Dave and I collaborated on really fully as, really we were just in each other's offices, like maybe 15 hours out of a week at that point in this work. And where we took on something that was tractable, but also instantiated something that we both felt was sort of much broader than the specific limitations of, context influencing the perception of a letter in a string of 4 letters. And I think it was a tremendous choice in that it was possible to develop this model that was explicit, understandable, analyzable, presentable to the whole field, while also resonating with a much wider range of issues. And, selecting the problem for both its tractability and its generality is, of course, that's easy to say, do the right thing,
Yeah.
But,
Okay.
Look for that, and look for that mentor who has a certain amount of wisdom and judgment to help guide you as you wade into this very exciting and interesting field.
It is exciting. Well, I know that you have to go, so James McClelland, thank you very much. And as per your request in your lectures online in the videos about the Mathematical Cognition Project, good luck.
Okay, thank you.
Brain Inspired is a production of me. You can support the show through Patreon for a trifling $2 or $4 per month. Go to patreon.com/braininspired or go to the website braininspired.co and find the red Patreon button there. Your contribution will help keep this show going without any annoying advertisements like you hear on other shows. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.
The stare